Hello, my name is Shania Navarro, and this is my video lab report for Lab 3 circuits. In this experiment, we used the FET Circuit Construction Kit Simulator to investigate the behavior of electric circuits with resistors and capacitors. The main objective was to understand how current and voltage behave in series circuits and how capacitors charge and discharge over time. The purpose of this lab was to predict the behavior of circuits that include resistors in series and parallel, and to use virtual multimeters to measure actual values of current and voltage. We also examined the behavior of ohmic resistors and capacitors and applied conservation laws, specifically charge conservation and energy conservation, to analyze these circuits. Throughout the experiment, we relied on several key physics concepts. First, Ohm's law, which states that voltage equals current times resistance. Second, Kirchhoff's loop rule, which tells us that the sum of the voltage changes around any closed loop is zero. Third, Kirchhoff's junction rule, which states that the total current entering a junction must equal the total current leaving. Finally, we use the exponential decay equation for a discharging capacitor. The voltage across a capacitor decreases over time according to the equation V equals V naught times e to the negative t over RC. We predicted the current using Ohm's law with a total voltage of 3.0 volts and a total resistance of 147 ohms. The predicted current was approximately 20.4 milliamps. In the simulation, both ammeters showed a current of 20.3 milliamps, confirming our prediction. We also measured voltage drops 0.95 volts across the 47 ohm resistor and 2.05 volts across the 100 ohm resistor. For simplicity, we assumed that wires had no resistance and all circuit elements behaved ideally. That means the batteries provided constant voltage, the resistors had constant resistance, and the ammeters had no internal resistance. We also assumed steady state conditions, meaning the current was constant in time. To check the loop rule, we added up the voltages in the circuit: 1.5 volts from the first battery plus 1.5 volts from the second battery minus 0.95 volts from across the 47 ohm resistor and minus 2.05 volts across the 100 ohm resistor. That gives a total of 0, which confirms energy conservation. We also plotted a graph of electric potential versus position in the circuit, showing how voltage drops at each component, which will be shown in a later slide. The system for the experiment includes the batteries, resistor, ammeters, and voltmeter, all components actively involved in the circuit. The environment is the simulated space in which we built the circuit. There are no external energy loss such as heat or sound modeled in this simulation. We had to use a real ammeter instead of a simulated one. It would have introduced some internal resistance. This could slightly reduce the current in a real low resistance circuit and slightly change our measurements. In contrast, the ideal ammeter used in the simulation has zero resistance, so it does not affect current flow at all. We connected a capacitor directly to a battery with no resistor. The ideal model predicts an infinite current spike because there's no resistance to limit the flow. However, in real life, internal resistance in the battery and wires would limit that current. As a result, the capacitor would charge very quickly but not instantaneously. In the second part of the lab, we observed how a 20 millifarad capacitor charges and discharges through two different bulbs. Using a 10 ohm bulb, the charge time and discharge time were both 15.2 seconds. When using a 20 ohm bulb, both times increased to about 30.6 and 30.7 seconds. This confirmed that the charging time depends on the product of resistance and capacitance, the RC time constant. A 9-volt battery, a 20 millifarad capacitor, and a 30 ohm bulb, we recorded voltage across the capacitor every 2 seconds for 20 seconds as it discharged. Plotting the natural log of voltage over time produced a straight line. From the slope of this line, we calculated the RC value of about 9.93 seconds. The expected RC was 6.0 seconds, so our experimental result was slightly higher. Some difference between the theoretical and measured RC values is expected. Real circuit components like light bulbs don't always behave as ideal resistors. Their resistance can change as they heat up. Also, the simulation may have some built-in lag or limitations. Even so, the result is reasonably close to the expected value and supports our theoretical model. Circuits are used in many real-world applications. These include timing circuits, camera flashes, signal processing processing systems, and low-pass filters. Understanding how they work is essential for designing electronics that depend on controlled charge and discharging time. In conclusion, this experiment confirmed that electric circuits follow the laws of charge and energy conservation. The behavior of resistors matched Ohm's law, and the behavior of capacitors followed an exponential time model. Simulation tools made it possible to gather precise measurements and better understand the underlying physics. Thank you for